And welcome back to Real Class. My name remains Engineer Shegun, and I'm your guide in physics. Here today, we'll be talking about simple harmonic motion, which is a follow-up from circular motion. Now, what is simple harmonic motion? A body is said to undergo simple harmonic motion when it fits in this criteria. Simple harmonic motion is a periodic motion. Simple harmonic motion is a periodic motion of the body along a straight line, such that the acceleration of the body is directed towards a fixed point, and that acceleration is directly proportional to the displacement of that from that point. Let me break down some few things I just said. First, it is periodic. When we say something is periodic, we mean something that repeats itself at regular time intervals. So I can also say it's a to and fro motion. Secondly, it has an acceleration, which is directed towards a fixed point. That fixed point is the equilibrium position or the center of motion. With that being said, what are the examples of body undergoing simple harmonic motion? A simple pendulum displaced at a small angle is undergoing simple harmonic motion. A mass and a spring system is undergoing simple harmonic motion. A diver's board is undergoing simple harmonic motion. A tuning fork is undergoing a simple harmonic motion. So these are the examples. Even a loaded test tube is also undergoing a simple harmonic motion. So these are some of the examples of bodies that are undergoing simple harmonic motion. Here in simple harmonic motion, there are some terms that are very, very important that we must know. Terms like amplitude. What do we mean by amplitude? Amplitude is the maximum displacement of the body from the equilibrium position. In this diagram I have here, this is an example of a mass and a spring system. The spring is at rest at this point, so this is my equilibrium position. If I hold this spring and pull it, drag it back to this point, this is the largest point I've taken it to. This is the maximum displacement from this equilibrium position. So that is my amplitude. Amplitude is the maximum displacement from the equilibrium position. The next thing is frequency. What is frequency? Frequency is the number of complete oscillations or number of complete cycles made per second, or the number of complete oscillations or the number of complete cycles it will make in 1 second. So from that definition, I can get a formula for frequency, which is N over T, where N is the number of complete oscillation and T is the time. N is oscillation, T is time, hence the unit of frequency is in hertz. Hertz as in H-E-R-T-Z, hertz. The symbol for that is Hz. Now, having said all of this, the next thing I'll talk about is period. Period is now the time it will take to make one complete oscillation. So period is oscillation, is time per oscillation. So the unit for period is seconds, because it's the time to take to make one complete oscillation. If you observe this equation very well, you will notice that frequency and period are the reciprocals to each other. So I can say that frequency F is equals to 1 over T, which of course I can also say that T is equals to 1 over frequency F. There are some important equations we need to take note of when it comes to simple harmonic motion. Now, for a body undergoing simple harmonic motion, it is accelerating back to the equilibrium position, which means that the velocity at each point along the path to the equilibrium position is not the same. Hence, the velocity at a certain distance from the equilibrium position is given by this equation. V is equals to W square root of A squared minus X squared, where A is amplitude and X is the distance from the equilibrium position. The acceleration of the body at a certain distance from the equilibrium position is given by this equation. Acceleration A is equal to minus w squared x, where w is our angular speed and x is our distance. Notice that there is a negative sign here. When solving, you do not need to include the negative sign. But the negative sign here tells us that the displacement and the acceleration are in opposite direction, and that is why there is a negative sign here. Now, it is important for you to know that these two equations can differ or can change based on the position of the body in the pan. Now, you should understand this, that there are two extremes you should also consider. These two extremes are the end of motion and the middle of motion. Remember, I told you that middle of motion is the same thing as the equilibrium position. You should know this, that at middle of motion, x is equals to 0, and at end of motion, x is equal to a. If x is equals to 0 at middle of motion, what will happen to our velocity at the middle of motion, which is the same as the equilibrium position? What will happen to our acceleration at the equilibrium position? Since x is equals to 0, recall that I earlier said that v is equals to w square root of x squared minus x squared. If this were to be the middle of motion, x is equals to 0. And if I substitute x to be equals to 0, this whole equation will break down to v is equals to WA. And this is my maximum velocity. So velocity is maximum at the middle of motion. If velocity is maximum at the middle of motion, you should also know that kinetic energy will be maximum at the middle of motion. Why will the kinetic energy be maximum at the middle of motion? Because there is a relationship between velocity and kinetic energy. Kinetic energy rather, is equals to half mv squared. Therefore, v there is our velocity, and if v is maximum, kinetic energy will be maximum. But recall that a is equal to minus w squared x. If we are saying that at the middle of motion, x is equals to 0, if I put x here, it means that I'm having 0 here, and 0 times anything is 0, which means that at the middle of motion, acceleration is equals to 0, there is no acceleration. Take note of that. What about at the end of motion? At the ends of motion, recall that I just said that at ends of motion, x is equals to a. And if x is equals to a at the end of motion, then what will happen to velocity at end of motion? What will happen to acceleration at end of motion? Velocity v is equal to w square root of a squared minus x squared. If this guy is a, if x is equals to a at end of motion, then if I put a here, you agree with me that a squared minus a squared is 0. Square root of 0 is 0. 0 times anything is 0, which means that at end of motion, v is equals to 0. There is no velocity at the end of motion. And of course, if velocity is equals to 0 at end of motion, kinetic energy will be equal to 0 at end of motion. But what will happen to the acceleration at end of motion? Recall that we earlier said that acceleration is equal to minus w squared x. So at end of motion, x is equals to a. So I'll have a to be equal to minus w squared a, where is my amplitude. At this point, this acceleration here is way larger than this acceleration here. So I will say that acceleration is maximum at end of motion. So if they say what is the formula for maximum acceleration, or if they ask you what is the maximum acceleration, or if they ask you what is the acceleration at the end of motion, you know that this is what you are to use, because at end of motion, acceleration is maximum. Now, if velocity is equals to 0 at the end of motion, kinetic energy is equal to 0 at the end of motion. it also means that potential energy will be maximum at end of motion, because potential energy is the opposite of kinetic energy. Both potential energy and kinetic energy are all forms of mechanical energy. So when kinetic energy is maximum, potential energy is equal to zero. And when potential energy is maximum, kinetic energy is equal to zero. So since at end of motion, kinetic energy is equal to zero, it simply means that potential energy is maximum at end of motion, acceleration is maximum at end of motion. At the middle of motion, which is the same thing as the equilibrium position, kinetic energy is maximum, so velocity is maximum, but potential energy will be equal to zero at the middle of motion. Now, I've told you that a simple pendulum undergoes simple harmonic motion. These are the important things that you need to know about the periods of a simple pendulum and the period of a mass and a spring system. For a simple pendulum, this is a simple pendulum. A simple pendulum undergoes simple harmonic motion if it is displaced at a small angle. So if I take this simple pendulum bob, I take it to this point and allow it to swing, it will go to and fro, undergoing a simple harmonic motion. Let's say we displace it at a very small angle. If you are asked for the period, this is the formula for period. This is the formula for the period of a simple pendulum. Period T is equal to 2 pi square root of L over G, where L is the length of the pendulum and G is acceleration due to gravity. So interestingly, if they ask you from this place, and they ask which of the following factor will affect the period of a simple pendulum, from what you can see, period T is equal to 2 pi square root of L over G. So you obviously know that length is going to affect what? The period, as well as acceleration due to gravity will affect the period. So length affects period and acceleration due to gravity affects period. But for a particular location in space or on the Earth's surface, a particular point on the Earth's surface, G will be a constant. So the only thing that will be affecting it will be length. You cannot say that mass will affect the period of a simple pendulum. The period is independent of mass because in our equation, there is no mass. What about this equation? What is it needed for? If a body, there's some kind of question whereby they will give you the period at a particular length and they'll give you the period at another length. And they will ask you to find one of those lengths or one of those periods. That's where I need this one. Where T1 over square root of L1 is equal to T2 over square root of L2. This one and this one are exactly the same. If you square both sides, you will end up having this one. And you can use both of them for the same questions. However, there are some questions whereby this one is much faster than this. And there are some questions whereby this one is much faster than this. If in a question, the two different lengths are given to you, then you are looking for one of these periods. One of them is given, you are looking for the other. This is way faster. When a question whereby the two periods are given to you, then one of the lengths you are looking for it, then this will be way faster. This is the period of a mass and a spring system. For a mass and a spring system, we have period to be equal to 2 pi square root of m over k, where m is our mass and k is the spring constant. Now, here, you must have heard of things like force vibration, you must have heard of things like resonance. Force vibration is a simple phenomenon whereby a body is set into oscillation due to another oscillating body or a periodic force. Now, if a body is set into oscillation and left undisturbed, that frequency it will vibrate with, it is known as the natural frequency. The frequency a body will vibrate with when set into oscillation and left undisturbed is the natural frequency. If I keep applying a force, a periodic force to a body, and that body is set into oscillation, that is force vibration. There is something called resonance. Resonance is said to occur if the frequency of the periodic force, coincides with the natural frequency of the body. At resonance, the oscillating body oscillates with a very large amplitude or with a maximum amplitude. With all of this said, there's a question JAMB has asked before, and they said, why is it that when soldiers are crossing a bridge, they cross through the bridge marching disorderly? The reason why soldiers crossing through a bridge will have to march disorderly is to avoid resonance. Because if they were to march orderly, their marching is order, their force is orderly. And that can coincide with the natural frequency of the bridge, which will cause the bridge to vibrate with a very large amplitude. That can cause the bridge to collapse. So if you see a question like that, the reason why soldiers would have to cross through a bridge marching disorderly is to avoid resonance. Now we are now going to look at some other questions that they can ask from here. Still on simple harmonic motion. This is our first question. The frequency of an oscillator is 4 Hz. If it makes 12 vibrations in t seconds, calculate the value of t. Vibration is the same as oscillation. Remember we said generally that the frequency of a simple harmonic motion is given by n over t, where n is the number of complete oscillation, or number of complete cycles, or number of vibrations, and t is our time. In this question, they are giving us frequency 4 Hz, so we know f is equals to 4. They told us that it made 12 vibrations, so n is equals to 12. We are asked to find time. If we plug in all of this, we are going to have 4 is equal to 12 divided by t. Cross multiply, we have 4t is equal to 12. Divide both sides by 4 to make t subject of formula. Then I would have t is equal to 12 divided by 4. 12 divided by 4 is 3. So our time is 3 seconds. Let us look at